last week we started a new topic called Moment of Inertia. And I mentioned that the reason I'm giving so much time or dedicating so much time to this topic is so that we can be really good at it. Even after we finish this class, we're going to be really good at it, and you won't be surprised or worried or concerned when you see it in your future classes. So we started with some theory and we did several problems, and we even did an extra problem in the review session. And this week I would like to focus on problems today, maybe homework problems. And on Thursday, we're going to cover the last bit of material that we need for this topic, and then finish off with more problems, or Wednesday, whenever the next class is. You'll notice that on the review sessions, I'm doing problems that I didn't do in the class. That's not because I want you to have to watch through hours and hours of video. It's just because I want you to have as much info available so that you can choose. Like, oh, maybe this problem is something that I want to see how it's solved. Okay, so it's not something that I want you to force you to have to watch everything. Just watch the lecture videos, the ones that you have to, but yeah, the review session will have different problems, and it's on purpose, right? Because I want to make sure we have as much material as possible. So let's go ahead and start working on some of the homework problems. This last homework, our first problem was 10.1. So let's just go look at it. It seems like a very simple problem. So I think it'd be good to start with this problem, 10.1. All right, and let me see which marker I want to use. I want to use this one. So let's start with 10-1. In this problem, we are given this shape on the xy plane. We have dimensions of A and B. And then we have the curve that is given to us by the equation y equals b over a to the power of n times x to the power of n. Pretty general equation. And we'd like to find the moment of inertia about the x-axis. Okay, so that's our first problem. Find the moment of inertia about the x-axis. Now, whenever we want to find the moment of inertia, of course, we want to know our limits of our area. You can see that this shape is bounded by the curves y equals b over an times xn, by the line x equals a, and then by the line y equals 0, which is just the x-axis. So we know the limits. Our first step to solve this problem is what?
Define your dA.
All right, you want to set a differential area, right? Set a differential element, dA. Now, we want to find the moment of inertia about the x-axis. So should our element be horizontal or vertical?
Vertical.
Why vertical?
Where's horizontal actually?
Horizontal. Why horizontal?
Because if you set it to vertical, you calculating that. I think it's not right. Go ahead.
I think it is vertical, right? Because dA can be parallel to x, right?
The differential dimension of dA cannot be parallel to the x-axis. So if you were to do it vertical, what's the differential dimension, the small dimension? Sorry?
Yeah.
And is dx parallel to x? Okay, so it cannot be vertical, right? Our element will be horizontal, because this differential dimension, in this case dy, is not parallel to the x-axis. Does that make sense? Okay, so we're going to have to set our differential element, and we're just going to draw a element at some arbitrary point xy in this curve, okay? Now let's make sure we remember that. The differential dimension cannot be parallel to the axis where you're finding your moment of inertia, okay? So we want to make sure that this differential dimension dy is not parallel to your axis. So right now we can use this because it's not parallel to the x-axis, okay? So we have our differential element dA. We set it at some arbitrary point xy. Then, as you already know, we want to find the coordinates of the centroid for that element. Now, we've been finding both x squiggly and y squiggly for this element. However, we know now that if we want to find the moment of inertia about the x-axis, then really we only need to know y squiggly. The reason we've been trying to find both is so that we can get some practice But let's work with what we really need right now. We only need the centroid of that element. And in terms of x or y, what is y squiggly? Just y. Good. Good, good, good. Then we want to set or express dA as a function of your differential dimension. So if I look at this area, what is this dimension equal to? dy. And what is this dimension equal to? A minus x. Jared, do you agree with that? That this is equal to a minus x? Yeah?
Yes.
Okay. A minus x. Remember, this whole thing is a. This part is x. So this is just a minus x. Does that make sense for everyone? Okay. Let me draw my element up here just so that we can see it a little bit better. This is a minus x. This is dy. So what is the area of that element equal to? A minus x times dy. So we get a dA. I'm going to write it up here so that we can see it better. dA is equal to a minus x times dy. Is this good enough for us to go and integrate? Why not? Exactly. You can see that as you move your element, as your y changes, your x changes as well. So that means that x is not a constant. It's actually a function of y. And because it's a function of y, we need to express this x in terms of my y coordinate. Okay? So we get that dA is a minus something times dy. Is there anything in this shape, in this figure, in this curve, that relates your x coordinate to your y coordinate?
Your function.
Can you say it again?
Your function.
Exactly, right? The curve equation. Okay, y equals b over a n times x to the power of n. So if we take that equation, I guess I'll have to write it here so we can all see it. Y equals b over a n times x to the power of n. If we take this equation and solve for x, what does that give us?
Y to the 1 over n over b to the 1 over n times a.
Noah, do you agree?
I would probably put it in a different form, but yes.
Just say yes.
Yes.
Good. Okay. So we have our expression for x. We see x as a function of y. Now I'm going to agree with Noah. Just easier for me to put all the constants on one side and then the variable on the other, but still correct. Okay. So I get that x equals all this. So x will equal a over b to the 1 over n times y to the 1 over n. And this is all multiplied by dy. Up to this point, we've pretty much solved the hard part of this problem, right? The last is just to integrate. But up to this point, are there any questions on how we got to this form? Yeah?
So just like in our previous problems, that function or that differential argument that created the one of dy, that is just how is it? That's the area of the small piece.
This dA is the area of this small piece.
And so, but that thing that we just wrote is equivalent to the a, and that's what we're integrating. Okay.
Yep. That's correct. This is all dA. Good. Any other questions? All right. The last step is to
Integrate.
There we go. Good. I'm glad that I don't have to ask for some emotion. Exclamation mark. We know that the moment of inertia about the x-axis is equal to the integral of y squiggly squared dA. That's given to us, and we already know that. And if we integrate this expression, we get the integral of, from step number 2, we get that y squiggly equals y, so this is just y squared. And then from step number 3, we get that dA equals all of this. So this is just all of this. A minus a over b to the power of 1 over n times y to the power of 1 over n times dy. And of course, we have our integration limits. Remember, we're integrating over the y-axis, which means that we need to know what's the range of the y coordinate in this shape. Noah, what's that range? What's the bottom point for the y?
It would be 0.
What's the top point for the y?
B.
Okay, so we're integrating from 0 to b. Is that correct, Ryan? Good. So we're integrating from 0 to b, all this expression, then what does this give us? I'm going to have to continue here. I get that the integral, and at this point, we're just having fun with math, right? The integral is just equal to y squared times a, so from 0 to b, a y squared minus, what do we have here? A over b to the power of 1 over n. What's y squared times y to the power of 1 over n?
2 plus 1.
Okay, so y 2 plus 1 over n, right? Yep. And all this multiplied by dy. Good. Now let's integrate. I'll take this one, and then you guys can take this one, okay? So let's go ahead and integrate. We integrate this. This is a over 3y cubed, evaluated from 0 to b. And what's this integral?
Maybe just looking at the y value, it
Uh-huh.
would be.
So I'm going to put my
7
constant here.
So 2 over 7, or n over 7 times y to the 7 over n.
I get what you're saying. I really do. Do you think maybe we may be complicating ourselves just a little bit? All right.
You're right.
Yeah, write it down. I think that'd be better. Write it down. Let's see what that gives us. Remember, don't think of this as, oh my God, we have all these weird things. This is just an exponent, right?
You multiply that by 1 over 3 plus 1 over n.
Okay. So we get all this plus 1, right? Let's look at this one. We get 2. So we just had a over 2 plus 1 times y to the power of 2 plus 1. So we should have the same thing here, right? Plus 1 times y to the power of plus 1. So I'm just going to say 2 plus 1 is 3 plus 1 over n. And all this multiplied times y to the power of that. Is that correct? Does that make sense? Okay. If we were to derive this, remember, we just multiply all of this here, cancels out, and then subtract 1 from this exponent, and we still end up with here. And of course, this is all evaluated from 0 to b. And let's go ahead and solve this. We get b cubed a, so a b cubed over 3. 0 just makes everything go away. Minus, oh, you're going to have to help me out here. A b to the power of 3 plus 1 over n over b to the power of 1 over n over 3 plus 1 over n. I think we can simplify this a little bit more, right? We still get a b cubed over 3 minus, what can I do here?
AB to the third.
Oh, thank you. So where did you get that from?
So 1 over n both cancel out.
Exactly, right? Remember, if you have a constant elevated to the power of an exponent divided by the same constant elevated to the power of exponent, all you're doing is subtracting the exponents, right? So this is just b to the power of 3 plus 1 over n minus 1 over n. So 1 over n minus 1 over n, you just get a b to the power of 3 divided by 3 plus 1 over n. And if you want to make it a little bit more simpler, you get a b to the power of 3 over, yeah, I guess, nah, I'll just do ab to the power of 3. Multiplied by 1/3 minus 1 over 3 plus 1 over n. And you can still do a little bit more, right? Get a common denominator, all that stuff. But I'll leave that up to you. Or we could also do it observed. I'll leave it up to you. Let's focus on what really matters here, which is moment of inertia. Up to this point, are there any questions? Actually, let's just simplify this more. I just don't like how it looks. It just doesn't make me feel so good. So we have moment of inertia about the x-axis equals ab to the cubed 1 over 3 minus 1 over 3 plus 1 over n. What can I do here? I can multiply this by n over n. So this will be 3n plus 1 divided by n. So that way my n goes all the way up here, right? So this is just n. There we go. And now I can multiply this by 3n plus 1, 3n plus 1. So this will be a, b to the cubed, 3n plus 1 over 3 times 3n plus 1 minus n. A, b cubed, 3n minus n is 2n. So 2n plus 1 over 9n plus 3.
Where did you subtract 3n?
Oh. Where?
On the
Where?
So when you multiply 3n plus 1 times 1 at the top left, and then you multiply 3 times the n.
Here?
Yeah.
But this is just common denominator. Oh, I see what you're saying. I should have multiplied this by 3 as well. You're absolutely right. So I get minus 3n. There we go. Oh, good catch. So 3n minus 3n is just 1 over 3 times 3n plus 1. There we go. Actually, that looks a lot cleaner. Looks a lot nicer. Thank you. Thank you. I appreciate it. All right. Any questions? I know I really didn't want to leave it like this. It just makes me feel bad in my heart. Any questions with this? You good, Chris, so far? Noah? Duong?
Yep.
Daniel? Luis? Kevin? Jared? Okay, good. Let's try the next one. We found the moment of inertia about the x-axis. Now let's find the moment of inertia about the y-axis. So we'll do 10-2. What we want to find now, I, y. As you can see, I'm trying not to have to draw so much, so I'm just erasing what I don't need. 2. This remains the same. 2. And then this all starts to change. Okay, so we want to find the moment of inertia about the y-axis. You already know, we've done this multiple times. We typically start our problems by setting a differential element with an area of dA. Would this element be a horizontal or a vertical element? If we want to find the moment of inertia about the y-axis.
Vertical.
Exactly, right? Because your differential dimension cannot be parallel to your axis. I just realized that I've been using the worst way of explaining. Instead of saying that, I should just say, choose your element to be parallel with your axis. I think that's easier to remember, right? If you want to find your moment of inertia by your y-axis, your element should be vertical. God, you learn something new every day. I'm glad I'm not teaching this class next semester. So we're going to do a vertical element, okay? So we draw a vertical element. Again, I'm exaggerating it. It's actually a very thin element. And what were the dimensions of this element? We know that this horizontal dimension is what?
dA.
Dx, right? What about this vertical dimension?
it is
Y.
So from here to here, how much do you have?
y.
There we go. Good. So we set a differential element. Do we need to find y squiggly or x squiggly now?
X squiggly.
X squiggly. And what is X squiggly? Just X. That's correct. We want to express dA. So we already know that the area of this element dA is simply the product of its two dimensions, y times dx. Tuong, is this enough for us to integrate?
No.
What do we need to do?
You need to find the y.
Exactly, right?
The y in the function.
Y is not a constant, right? It changes. So we want to express this y in terms of x. Graham, what's y here? If I want to express y in terms of x, what is that?
B over A to the B to the n.
Mm-hmm.
X to the n. Yeah.
Good. So we've expressed our differential area in terms of x. And now the final step is to
Integrate.
Thank you. At first you sounded excited, but now you sound miserable. It's like you're miserable trying to sound excited. But it's okay. We'll fix that eventually. Okay, moment of inertia about the y-axis, as you know, is the integral of x squiggly squared dA. From step number 2, x squiggly is just x, so the integral of x squared. From step number 3, dA is just b over a to the power of n times x to the power of n times dx. And what are my integration limits? 0 to a, that is absolutely right. Those are my integration limits, or limits of integration. Okay, so from 0 to a, I'm going to have my constants b over a to the power of n. What's x squared times x to the n?
X to the 2 plus n.
Exactly. Good. So let's go ahead and integrate. My constants come out. Nothing changes there. What's the integral of x to the power of 2 plus n?
X to the power of 3 plus n over 3 plus n.
That is absolutely right. And we evaluate this from 0 to a. I think at this point we can solve, right? B times a to the n. A to the power of 3 plus n. 3 plus n. A to the power of 3 plus n over a to the power of n is simply a to the power of 3. So I'll just say a to the power of 3 times b divided by 3 plus n. Good. Any questions? Yeah?
With these types of problems, is it more common for the solving for the moments of inertia to mathematically work out to a prettier answer easily in one dimension compared to another? So rephrasing
So I think I understand your question.
This one was a lot easier to simplify.
The answer is yes, but I don't know how I can look at it and say, this will be easier or cleaner in this direction. I wouldn't know how to find it. Maybe someone that's more math oriented can look at it and say, yeah, the moment of inertia about this axis. One thing I do want to make sure we talk about. Typically, you'll get cleaner equations, and this is not a given for everything, but you'll get cleaner equations when notice that you can notice that your x-axis here actually starts with the entire shape and then starts to decrease. Your y-axis is the opposite. It starts low and then starts to increase. I've noticed that there's some correlation between that and how clean your equations look, but I don't think that's a rule. I really, really don't think that's a rule. So I don't want to say that it is, okay? Any other questions? Good. Okay. How much time do we have left? Okay, so let's move on. Let's go with 10-3. I can use this part of the board. I don't have to keep erasing. Okay, so for 10-3, what do we have? We have this shape given in the xy plane. And this shape is a parabola. Nice. Parabola is given by the curve y equals 1 over 50 x squared. And this, I'll just call it a radius. It's not a radius. This width is 100 millimeters. And this height is 200 millimeters. Technically, I just need to give you one dimension because you can use the equation to find the other. But you have what you have, okay? It is what it is. Let's find the moment of inertia about the x-axis. Now, we've already done two problems where I've walked you through the problems. I would like for you to walk me through this problem. So begin.
Start by. Go.
So the differential minus dA. At x1. So if it's Ix, then it would have to be horizontal shape.
Like this?
All the way to the
All
left
the
side.
way.
You want it all the way? Okay. If you say so.
So I do have a quick question about these kinds of problems where we're symmetrical along an axis.
Mm-hmm.
Can we just cut it in half and multiply?
I don't know. You guys, you're the ones that are leading me. So what do you think? Would it make sense to solve only for half of it and then multiply by 2, since we're talking about moment of inertia?
If it's the same on both sides, then yeah.
So let's recall, remember when we were talking about composite moments of inertia? You know, we had different shapes. All we had to do was find the moment of inertia for the individual shapes and then add it up, right? So what we're doing here is we've got to find the moment. We can say that we're finding the moment of inertia for these two individual shapes and adding them up. Now the question is, does the symmetricality, I don't even know if that's a word, but does the symmetrical, nature of these two shapes, does that mean they'll have the same moment of inertia? What do you think?
I think it depends on the axis. Since it is based off of the x-axis, in my mind, the pressure or whatever the moment of inertia is, it's the same going down. Maybe a negative will be in there, or being going across the negative axis, or heading in the negative direction. But finding for Ix, it will be the same, but solving for Iy, it is not symmetrical in that dimension.
I like it. I like what you said. Let's see if that's true. Okay? So let's solve it the way we normally solve it. And then let's see if that's actually equal to twice the moment of inertia of only 1/2. I think it will be, just like I agree with Noah. I think it will be. But don't take my word for it. Let's do it ourselves. Okay? So we set our differential element. Continue guiding me.
Okay, so then next step would be to find only y squared was only x squared. And y squiggly is just 1. And then the next one you express dA in terms of x and y.
I would say that dA equals 2x. dy.
Are you starting to see a relationship between this and what you asked about?
I am, because the length of x is double because of the axis.
So when you integrate this, right, you'll have the integral of 2x dy. Move the 2 to the outside, and you get twice the integral of x dy. And what is the integral of, x squared? Here, you have 2x dy, right? You can have the integral of x squared, there we go, times 2x dy. Factor out the 2, and then you're going to have twice the integral of x squared times x dy. Now the question is, does that actually correspond to the integral of just one of these sides, or doesn't it?
I'm not entirely sure. So.
Okay, no problem. So we express dA. Let's move on.
So then you integrate. No, but you have to put x in terms
Ah, there we go. How do I do that, Tuong?
So y equal 1 over 50 x squared, so x is equal to square root of 50 y.
Okay. Like this? All right, let's move on.
So then you
Can you say that again, but with a little bit more?
integrate
There we go.
A
the integral of y squiggly squared dA into just the integral of y squared to root 50y dy.
I'm gonna separate these two. Actually, I'm gonna express the y in terms of an exponent just so it's easier for us to integrate.
And that's from 0 to 200. And then you can take the 2 root 50 out since they're just constant. And then your 0 to 200 is the same for the integral, and then you can add the y squared and the y 1/2 exponents together to get y to the 1/2 over 2.
Like this?
Yeah.
Okay. Or like you said, pi over 2.
Equal. And then you just
2 times 25, right, is 50. And then the square root of 25 is 5.
that's going to be 10 root 2.
This looks nicer than 2 root 50.
you get 2/7 times y to the 7/2 from 200 to 0.
0 to 200.
From 0 to
Do you want the answer for that?
Yeah.
Or like just 4.57 times 10 to the 8.
Let's use powers of 3 for our exponents. So 10 to the 3, 10 to the 6, 10 to the 9.
457 times 10 to the 6
Okay. Units?
millimeters. To the 4th. I don't
That's
know what
correct.
called.
Millimeters to the 4th. Good. Good job. Notice that with little to no interaction from me, you have solved the problem on your own. This is good news, right? This means that we are ready for that take-home exam. How much time do we have left? Are we done?
You have 40 minutes.
My goodness. I think we're moving a little bit too fast.
Can we do 10/9?
Yeah, please.
Okay.
Actually gonna ask that. Can we do like composite after that? Too?
Yeah, sure. I mean, this class is for you. I mean, you're paying for it, right? But after you pay for it, this class is for you. So 10/9, right?
Yes, sir.
Let's see. We have our x-axis. We have our y-axis. And then we have this thing. Is that a half circle? I don't think it's a half circle. The equation is y equals 2.5 minus 0.1 x squared. It's not a half circle.
It's like an ellipse, though, isn't it? Or a half ellipse.
I don't know. So the equation for an ellipse, right, is y squared over something plus x squared over something equals something squared. Here we only have a y. There's no root of x squared. So it's just a parabolic equation. It's a parabola. It's a section of a parabola, upside down, okay? This is 2.5. We want to find the moment of inertia about the x-axis. We want to solve this problem in two ways. Using rectangular elements having a thickness dx and having a thickness dy. Ooh, I like this. I like this. We're going to have to do both different ways. Now, you know that if we want to find the moment of inertia about the x-axis, then using an element with thickness dy is pretty much warranted, right? But then if we want to force ourselves to use an element with thickness dx, then we're going to have to maybe apply some of the other things we've learned in class, okay? So let's go ahead and solve this problem. All right. Step number 1, moment of inertia about the x-axis, okay? And we're going to solve it in two different ways. We're going to solve it by using an element that has a thickness of dx and using an element that has a thickness of dy. Let's start with what we already know, element with thickness of dy. That way we can kind of warm up a little bit and know what answer to expect, okay? So we start with this element, or we start with this shape. Our first step is to set a differential element, dA. Now we're going to start with the easy one. If we want to find the moment of inertia about the x-axis, we want an element that's parallel to the x-axis, right? So that the differential dimension is not parallel to the axis. So I'm going to start with an element dx.
I have a question.
Yeah?
On these types of, for the moments of inertia, will all the problems I shouldn't say all, will a majority of the problems we face when we solve for the centroid, the y squiggly, will all that be equal to just y for these types of problems? Okay.
For moment of inertia, yes. Not for centroid.
Gotcha.
For
I can't remember what the term was for these.
Yep. Good, so we have our element. We know that y squiggly equals y. And again, the reason I include this is not because I want you to do extra work, is because I want to keep the same routine that we use to find centroids. And for centroids, this is an integral part, right? And I don't want to, it's pretty much the same. And I want to keep forcing on you the idea that it's the same, so you don't feel that you're doing two different things, right? So we set this differential element. What's this height of the element? What's the length or width of this element?
2x.
Okay, so dA should be equal to 2x times dy. Is that enough to integrate?
No.
What do we need to do? We need to express x in terms of y. What is x in terms of y?
The square root of y minus 2.5 over 0.1.
Like that?
Yes.
All right. And then this multiplied by dy. Good luck integrating that. 25?
Yeah.
Okay.
Is that correct?
What?
Shouldn't there be a negative somewhere?
No,
in
it
there?
should be 2.5 minus
Oh, yeah, I think the same.
Should be
Ah.
minus one.
Look at me following you blindly.
Ooh.
I'm kidding. I did not realize it either. So 2.5 minus y. Like this, Jared?
I would agree. Yes.
Okay, there we go. So we get square root of 25 minus 10y dy. Let me simplify this a little bit more. 25 is 5 times 5. 10 is 2 times 5, right?
Yep.
But then we still have square root of 5. Okay, that doesn't really help me. Ignore that. Yeah, I guess we can just leave it like that. Good. I'm not going to make you say it this time. So we get that our moment of inertia about the x-axis is equal to the integral from where to where?
negative x. No, sorry. 0 to 2.5.
It's from 0 to 2.5 of y squared, y squiggly squared. We know that y squiggly is just y times dA. We know dA is just 2 times square root of 25 minus 10y multiplied by dy. And let me just write all the steps here so that we can be consistent. Integral of y squiggly squared dA. Good. Let's take out the constants. Well, just 2. We have the integral from 0 to 2.5 of y squared. And I'm just going to write this in exponent form. What's that integral?
25 y squared minus 10 y plus 9. Wait, what's the derivative? Well, somebody that knows.
Can you just put it in your calculator? So I don't think you can simplify that, right?
According to my integral, and I want to trust this because I use a website called Wolfram Alpha. Have you heard of it?
No.
Such a good place, such a good website. According to that, it's a lot, right? It's negative y squared over 15 times 25 minus 10y to the power of 3 halves minus 2y over 375 times 25 minus 10y to the power of 3 halves minus 2 over 13,125 times 25 minus 10y to the power of 7 halves. Nice, nice. Well, remember, it's your job to know how to integrate. I already learned and I already graduated, so it's not my job to know. All right, so let's just go ahead and solve it with what we have. So we have the integral, right? Up to this point, that's what we need to calculate the moment of inertia. And that integral yields negative y squared over 15 times 25 minus 10y, so over 15. Okay. Minus 2y over 375. Minus 2 times 13,125 over 13,125. 25 minus 10y to the power of 7 halves from 0 to 2.5. Again, and I think if I haven't made it clear right now, and let me just rephrase, right? My intention here is not to test how good you can integrate, but I strongly recommend that you at least have an idea of where these integrals are coming from. Once you graduate, your boss is not going to tell you, hey, solve this integral. If not, you're fired. Nobody will. You know where to find your integrals. And I do want to make a little bit of a tangent here. One mistake that I did when I was in college is to think in terms of, what are the ends, right? Not the means. What are the ends? And I thought that made me a practical person, right? I think about results. And one thing I learned after graduating, working, and becoming as dashingly successful as I am now, not really that successful if I'm here teaching, but one thing I have learned is that mentality, as a mentality, right? As a mentality, is not good. Okay? So you may think of, why do all students learn algebra before graduating high school if not all of them are going to use it? It's not because you want everyone to know the Pythagorean theorem. It's because the skills that you learn from using it can be applied into your life, right? The idea of analytical thinking. So I don't want to say memorize these integrals, learn how to solve all the integrals. That's not what I'm saying. In the end, from a practical point of view, you're not going to have to solve them. but I need you to know at least where they're coming from. I need you to know that they make at least some sense to you. If you're not sure where they come from, just derive this expression. If you can derive this and land at this, then at least you know that the integral is correct. But try to know where your things are coming from. Even if you don't know how to calculate them exactly, know where they're coming from, and I can guarantee you that they will make you a better engineer. I think we're still too early in our bachelor's trajectory to give you some more concrete examples. But I will say, I teach a class called Fluid Mechanics, and again, it's a really hard class. And knowing those principles, like knowing them really, really, really well, is what helped me start my own business. Because while everybody else that was pretty much along the same level of experience as I was, all they knew was to punch numbers into a program and calculate results, I actually understood why or how those results were being calculated. And that gives me a better idea of how to deal with the problems that I solve. Okay? So again, sorry for that little tangent. I don't have to apologize, I'm the teacher. We had a little bit of a tangent, but I do want you to understand. It's not that I want you to solve these integrals, but I at least want you to understand where they're coming from, if they're coming from somewhere, okay? Don't just copy them blindly and call it a day. So we solve this, we plug in our numbers. Let's see, for the case of y equals 0, all this is 0, so we don't care. For the case of y equals 2.5, you plug in 2.5 in here, plug it into your calculators, you solve it. And if you look at the back of your book, you get your answer. Because unless one of you wants to plug it into the back of your calculator. I guess it doesn't make sense that I gave you the speech and then just say, look for at the back of the book. Let's plug it into our calculators. Let's do a little bit of work here, okay?
I got 23.81.
All right, can somebody confirm that number?
Yeah.
Millimeters? No, feet. Feet to the power 4. Good. Good. All right. That was only one way of solving this problem, right? Are there any questions with how we solved it this way? Yes?
So this is more conceptual. I can understand what cubic feet is, but my brain doesn't really understand what feet to the 4th means.
So remember, when we're talking about moment of inertia, like I mentioned, it's really hard for me to explain what moment of inertia is. But you need to know that it's essentially related to not just depth, but area. So this feet to the 4th is not a physical measurement. It's not a physical quantity. It's a mathematical one. It's a mathematical one that comes from multiplying your area times your distance between your axis and centroid, right? So the best way we can explain it is just by doing that pressure example that we did at the beginning of this topic. But other than that, there is no, there's no way for me to explain it. I would just YouTube, search on YouTube. Maybe somebody can explain it much better than I can. But this part is somewhere where I'm just not good at. Like I don't know how to visualize it either. Okay, but I will say it's not as complicated as you think it is. So it's not like we're looking into this 4th dimension world or something. It's not that. It's just area times length times length. Okay. All right. So are we ready to do it the other way? Okay. So we solved this problem by drawing an element, a horizontal element, so an element that had a differential dimension of dy. But now, let's solve this problem by drawing an element that has a differential dimension dx. Now, if we do that, we run into a problem, right? Do we know what that problem is? What happens if our element has a differential dimension dx?
And it will be parallel with the axis that we're measuring.
Is that correct? Okay. So if we were to draw an element that's vertical, that has a differential dimension dx, that differential dimension is parallel to this axis, and we were to follow all these steps to the letter, we will not get the answer that we're looking for, which is 23.8 feet to the power 4. Is that correct? Okay. So what do we do? Well, we talked about different techniques, right? And there was one technique that allowed us to relate two axes that were, relate the moments of inertia between two axes that were parallel to each other. Does anybody remember what that was?
Parallel axis theorem.
That is absolutely right. The parallel axis theorem. Okay. So if we were to use the parallel axis theorem and we were to find, right, the moment of inertia for a differential element that's along the centroid of x, so that passes through an axis, or that is through an axis that passes through the centroid of this element, then we could use that element, or that moment of inertia, and then apply the parallel axis theorem in order to convert it into the x-axis. Now, when we use the parallel axis theorem, you may have recalled that we typically chose simple shapes like rectangles and stuff like that, where we already knew the moment of inertia. Here we don't really have a simple shape that much. But the concept behind the parallel axis theorem should still apply. So let's first start by drawing our element. Okay? And once we draw our element, we need to understand that we're going to have to select our x or y coordinates based on the axis, right? On the axis where we are trying to find the moment of inertia for that element. Noah, in the end, we want to find the moment of inertia about which axis?
About the x-axis.
Okay. Now, if we were to use the parallel axis theorem, right, then we would find the moment of inertia about an axis that passes through the centroid of my shape. Is that correct? Because does the parallel axis theorem require us to find the moment of inertia about the centroid of the shape?
I believe so.
Okay, good. So let's go ahead and apply the parallel axis theorem. Now here, like I said, because we have the situation where we're trying to find moment of inertia about the x-axis, but we are forced to use a vertical element. Did anybody write that answer just in case? Okay, good. Because we want to find that moment of inertia, I think it's a little bit easier if we look at the equation for the parallel axis theorem and see if we can use it in order to get to our answer. So the parallel axis theorem tells me that the moment of inertia about the x-axis is equal to a y squared plus, y bar squared, plus the moment of inertia about a axis that passes through the centroid of the element. And if you look at this, well, this is the moment of inertia about this axis. This is the area of the element. This is the y bar is the distance between your axis and the centroid of the element. Let's just say the centroid is here, just for the sake of it, right? And then this will be the moment of inertia about an axis that passes through that center. So if we were to find this moment of inertia, again, this element, this shape wouldn't really help us that much because this is still parallel to the axis. But what we can do, and this is something that I was hoping to cover on Wednesday, but I didn't realize that the homework that I assigned last week actually already includes it. We're going to deal with this in more detail. What we can do is we can take the parallel axis theorem and we can apply it to a differential element. In other words, this is the moment of inertia for the whole thing, right? This is the area of the whole thing. This is the y bar, so the distance to the centroid of the whole thing. And this is the moment of inertia for the centroid of the whole thing. What we can do, right, is to do a differential analysis. So remember, we do differential analysis to find centroids, to find moments of inertia, and we can also do a differential analysis to apply the parallel axis theorem. In other words, we set a vertical differential element, with a finite vertical distance, and then a differentially small horizontal distance, and then apply the parallel axis theorem, but only for that vertical element. So this is a tiny, right? Really thin differential element with an area dA. Then the moment of inertia about the x-axis for this tiny element, we can just call it di, right? So this is the moment of inertia for this tiny element, okay? And this is equal to the area of this tiny element. What's the area of that element? Just general, don't give me numbers. What's just the area of that element? dA, okay? times the distance to the centroid of that element. This is a y bar. Would this distance be a tiny value as well? Distance to the centroid of this element? No, right? It's a finite value. So it is there is some value here, okay? Now, if I want, let me take it step by step. I'll just call it y I squared. I was gonna just convert this now, but maybe let's take it step by step.
So you said that to determine the moment of inertia using the parallel axis theorem, we use the centroid, but will we ever be asked to determine the moment of inertia for rigid bodies that aren't uniform in their density?
So yes,
okay.
but not yet. So we're gonna cover a topic on Wednesday called the mass moment of inertia, and that's where we'll look at different, basically non-uniform elements. Okay, so we'll get to that. Don't worry. But right now, what we're doing here is we're solving this problem because this problem asks us to solve it with both a horizontal and a vertical element. We already did horizontal, and now we're just trying to find a way to do it vertically. Okay, this is a little bit new, but anyway, the differential moment of inertia for this tiny element, right, is equal to the distance to the centroid of this tiny element times the differential area dA, plus, and of course, I'll have the tiny moment of inertia about the centroidal axis for this element. So plus d I bar x. So at this point, does this differential expression make sense for this element? Or do you think there are some terms that we still need to perhaps modify or are not correct?
This could very well be wrong, but it seems like I'm going to stop that thought because it seems like it'd be wrong.
It's okay, we can all be wrong here.
I would think because I of x is in terms of x,
Mm-hmm.
you want your y bar to be in terms of x as well, but I would understand that with the equations to solve for I of x, you use y squared. So possibly not, but just an idea.
You're actually onto something here. Because, Jared, the reason this problem cannot be solved in the same way we've solved every single other problem is because this differential dimension dx is parallel to the x-axis. So we can't just apply those things. So if my differential dimension is parallel to the x-axis, right, that means my differential dimension is dx. We're going to have to integrate over dx. And if we're integrating over dx, we want everything to be in terms of x, not y. Okay? All right. So we set our differential element, or our differential equation. That's not a differential equation. We set our differential form of this equation, right? A tiny, infinitesimally small parallel axis theorem, but just for this element. And now what do we have? We get that this tiny moment of inertia about the x-axis is equal to the distance to the centroid of this element. Where's the centroid of this element?
It is
Okay, at the center, right? And this is actually what? Y over 2, right? Because this is y. So this is just half of it. Does that make sense so far? Okay, so I can say that this distance to the centroid is just y over 2 squared dA. What is dA here? What's the area of this element? First off, what's this length?
dx.
And what's this height? Good. So what's my area? Y dx, that's correct. Good. And now I want the moment of inertia about the centroidal axis. Now here is where we can now simplify everything into simple shapes, right? What shape is this?
Rectangle.
What's the moment of inertia about the centroidal axis for a rectangle? You're going to memorize it. I can guarantee you that you're going to memorize it before the end of the class.
dh to the third over 3.
Oh, centroidal axis.
12
Sorry?
over 12.
Okay, 1 over 12. Base times height to the power of 3. What's the height? Y. And what's the base?
Yeah.
Good. And of course, can we integrate now?
No.
Why not? Yeah,
Why is that y cubic?
this one?
Yes.
Because the moment of inertia for a rectangle about the centroidal axis is 1 over 12 bh cubed. bh. Okay.
Thank you.
Why can't we integrate?
Because there's a y and it's dx.
Exactly. I like your enthusiasm. Is there anything that relates this y variable to this x variable?
They function.
There we go. Right?
Yes.
So we get y equals 2.5 minus 0.1 x squared. All this divided by 2. All this squared times y. And y equals, I'm just going to call this y cubed. Okay? Cubed over 4 dx. Is that correct? Okay. Plus 1 over 12, 2.5 minus 0.1 x squared cubed again. Yeah, dx. Let's factor out, right? We get 2.5 minus 0.1 x squared cubed over, we can just factor out the 4 times 1 plus 1 over 3 times dx. Is that factorization correct? I factored out this and then just the 4. I think that's correct.
So, yeah.
What's 1 plus 1 over 3? 4/3, right? So the 4 cancels with the 4 over 3. So 2.5 minus 0.1 x squared to the cubed over 3 dx. So my dix equals all this. All right? How is dix, the moment of inertia for just one element, how is that single moment of inertia related to the complete or total moment of inertia for the entire element?
Integrate.
Exactly, right? What's the integral of the something? Something, right? Okay. So if the moment of inertia about the x-axis is equal to the integral of the moment of inertia for the little thing, then we just have to integrate this expression. So this will be just the integral of 1/3, 2.5 minus 0.1 x squared cubed dx. And then because we're in the x-axis, what are my integration limits?
-5 to 5.
-5 to 5. Good. This is actually not that complicated of an integral to solve. It's just going to be a lot of math, right? We're going to be multiplying a lot of stuff together. So let's just raise this to the cube. I'm going to take it the long way. I'm just going to raise it to the square first and then multiply by itself again, okay? So we get 1 over 3rd. Let's see, 2.5 squared. How much is 2.5 times 2.5?
Would it be smarter? Would it be easier to take that 1/3?
Yeah, I like that word.
Would it be easier to take that 1/3 out of the integral now, or?
Yeah, let's do that. All right, 2.5 times 2.5.
6.25?
I don't know. I'm honestly asking.
6.25.
Okay. All right, 6.25. Okay. 2.5 times -0.1 is -0.25 minus -0.25 is -5, right? -0.5 x squared plus 0.01 x to the power of 4. And all this multiplied by 2.5 minus 0.1 x to the power of 2. Is that correct? I'm just multiplied this by itself, but then I still have one more left because it's cubed. Does that make sense? Okay, good. And then the x. And now I can multiply one more time. 1/3 integral from -5 to 5. 2.5 times 6.25.
15.625.
So I get 15.625. So 0.1, so negative 0.625x squared. So this is 6.25 times negative 0.1x squared. Good. Minus. What's half of 2.5? It's 1.25, right?
Correct.
So negative 0.5x squared times 2.5 is negative 1.25x squared. Negative 0.5x squared times negative 0.1x squared is positive 0.05x to the power of 4. 0.01x to the power of 4 times 2.5 is 0.025 times x to the power of 4. This is positive. 0.01 times x to the power of 4 times negative 0.1 times x to the power of 2 is negative 0.001x to the power of 6. And all this multiplied by dx. Good? All right. I think at this point the integral suddenly became very easy, right? All right. So let's go ahead and integrate. Well, actually, let's simplify a little bit more. Moment of inertia about the x-axis is 1/3 integral from -5 to 5 of, let's see, how many integers with a variable? Just 15.625. Numbers with a variable. 15.625. Let's see. Negative 0.625 minus 1.25. How much is that?
Negative 1.875.
And this will be times x squared?
That is correct.
Okay. Is x to the power of 4? Do we have more than one term?
No.
Yep. Okay, so 0.05 plus 0.025.
That's 0.075.
That's correct. And finally, x to the power of 6 doesn't have anything else, so negative or minus 0.001 x to the power of 6, and all this multiplied by the x. And at this point, I think we can integrate. We get 1/3. Let's see, the integral of 15.625.
15.625x.
Okay. Minus 1.875/3 x cubed plus 0.075/5 minus 0.001/7 x7, and all this evaluated from -5 to 5. Okay. Start to plug in numbers. 15.625 times 5 minus 1.875/3 times 5 to the cube plus 0.075/5 times 5 to the power of 5 minus 0.001/7 times 5 to the power of 7. Before we keep writing down, just a suggestion. All of these 5s are elevated to powers that are odd numbers, right? What that means is that -5 to this will just be equal to -5 to the cube is the same as -5 cubed. Is that correct? Which means that if we're subtracting the negative versions of everything, it's the same as adding everything by itself, right? Just factor out the negatives and you just get plus, right? So what I'm saying is, whenever you insert a -5 here, all you're doing is changing the sign, right? If you factor out that -1 and you get minus -1 times the same thing, minus times -1 plus. So really what you're doing is you're just multiplying all of this times 2. Okay, I just want to avoid having to write everything down. All right, so just want to make my life easier and yours as well. All right, punch these numbers into our calculator and let us hope that we did a good job. Okay? What does it give?
It gave us to 23.1.
23.1?
Yeah, 23.81.
There we go, 81. Feet to the power 4. Can somebody confirm this value?
Yes.
All right. We did it. I did it. And I taught you. Did you learn?
So much.
I did it. Good. If you learn, it's thanks to me. And if you don't learn, it's your own fault. I think that's how it works, right? Okay. Any questions with that? I know it was a hard problem because we were forced to use a vertical element. But here, the same logic still applies, right? Parallel axis theorem and just anything, right? If you're in doubt, you can always do a differential analysis. We're going to do a lot more practice on that on Thursday. So don't worry too much about the procedure. We're going to do different examples on Wednesday. What time is it?
7:43.
So are we done?
Yes.
Good choice of problem. Who chose it? Jared and Tom? Ryan and Jared?
We both had it.
All right. Good choice. Good choice. I'm going to try to find more like these instead of just going in order for on Wednesday, okay? All right. If you haven't sent me your practice exam groups, take-home exam groups, make sure you send them to me. If I don't get your groups, I may be forced to put you with someone else that you don't know. And I want to avoid that. I want to make sure that you know who you're working with, because this will be, it's not going to be a super easy exam, right? It's going to take a little bit of work, okay? Yeah?
For the next class, could we do some of the Thompson area problems?
Yeah. Send me.
I don't think we've done any yet in the homework.
Okay.
For this week.
All right, I'll look into it.
Some actual ones to be.
Yeah.
Get more familiar with.
Sounds good.
Conceptual.
Sounds good. All right.